All right, hello and welcome to Office Hours. Um, hey there, Kate. Um, Tonight is super freeform. I don't have any pre-prepared material, so I am, as always, down to answer any questions. I don't believe I was checking my email earlier today and I didn't see um, any email requests. Awesome, Kate. I am glad to hear it. Like I said, I at least as of the last time I checked, which was maybe about an hour ago, I have not received any email requests for office hours. So you're good to fire away. Let's see. Great question. Um, as of right now, I do not know. Um, However, I would if I were to guess, I would say I'm probably not teaching 401. Um, but I don't know for sure. Mostly because our department chair has been out on paternity leave for the first half of this semester, and the chair is the person who sets the schedule. So, the schedule for the spring semester has not been set. So as of right now, I could be teaching anything. I don't know what I'm teaching, but typically, in the spring semester, at least in past semesters, they've had me teach 400 lecture and 420 lab. But who knows? Anything's possible. But that hasn't been the case in the past. Awesome, Ludwig. I can totally take your questions too. It is a open forum. I'm an open book tonight. Yeah, totally. 401 is a ton of fun though. I've heard really good things about both Dr. Green and Dr. Mahoney. If you're looking for someone, I've heard um, excellent things about them. I haven't heard Dr. Green lecture. I just know him on a personal level. I have sat in on Dr. Mahoney's lectures, and they are awesome. Yes. You absolutely can, because 760 millimeters of mercury of pressure is 1 atmosphere of pressure, and that is an exact unit conversion. So that is totally a solid unit conversion to use. let's see. That is a good question. That is an excellent question, and the answer to it actually lies in the equation. And so specifically, I'm gonna add something to the question. I'm gonna add why does the gas's density decrease with increasing temperature? And Isabel, after I answer this question from Kate, I'll hit up. Oh, sorry. I've got a question from Ludwig about the Hess's Law problem, and Isabel, then I will hit up your question. Sorry, Ludwig, I just saw your question. Now I'm going to finish answering the one that I wrote on the board. Then I'll hit yours, and then Isabel will get to yours. Okay. So why does a gas's density decrease with increasing temperature? So this is going to be a multiple steps to get to the answer. So first, when you look at totally, and I appreciate you being patient as well. When you look at the equation for density, density is a ratio of mass to volume. Now, here they're asking us about density and temperature. So really, we need to understand the connection between temperature and volume if we're going to answer this question. When you look at the ideal gas law, if we just want to zero in on volume and temperature, all right, we're going to say pressure and moles are constant. All right, if pressure and moles are constant, then they cancel out of this expression, and it simplifies down to just V1 over T1 equals V2 over T2, all right? And this equation comes from the fact that the volume of a gas divided by the temperature of a gas is equal to some constant number, right? Now, if you take this expression, I'm going to scoot it over because I need a little room to work here. And I'm just going to get rid of the denominator because things are easier to evaluate without denominators cluttering things up. We get an expression here that says volume is equal to some constant number times temperature. This shows that volume and temperature are directly proportional. All right, that means that if temperature increases, volume will increase. If temperature decreases, volume decreases, right? The two track with each other. So let's keep that in mind as we move to this next level of analysis. So we want to compare temperature of a gas and the density, which is mass over volume. If temperature increases, volume will increase, but because volume is in the denominator for density, an increase in volume means that you will experience a decrease in density. That is why the density of a gas decreases with increasing temperature. When you increase temperature, it blows up the volume, and volume is the denominator of density. So as volume grows bigger, the density will grow smaller. So a little bit of a conceptual take, but that is where the answer to your question lies. All right, Ludwig, you wanted to see the problem that I left at the end of lecture. Give me 1 second as I pull it up. Here we go. All right, okay. Let's pull this up. Kate, you are so very welcome. Ludwig, I am going to do your request now, which is for the problem that I left off at the end of lecture. So we want to know what the delta H, oops, let's get in the right layer here. We want to find the delta H for this reaction, the reaction between solid carbon and water vapor that produces carbon monoxide gas and hydrogen gas. All right, so this is kind of our guiding light. This is what we are trying to go for, and we've been given this array of reactions. So we've been told that the combustion of solid carbon produces carbon dioxide, and this is a delta H of negative 393.5 kilojoules per mole. We've been given the combustion of carbon monoxide gas. So carbon monoxide gas reacting with O2, producing carbon dioxide. This has a change in enthalpy of negative 566.0 kilojoules per mole. And we have the combustion of hydrogen producing water. This gives us a delta H, or has a delta H of 483.6 kilojoules per mole. All right. Hang on. Sorry, I'm going to have to rewrite this last equation. I meant to do it in a different layer. Here we go. Sorry about that. Here we go. So this is 2 molecules of H2 reacting with O2 to produce 2 molecules of water. All right. Okay, now let's talk tactics. Let's talk strategy. So we have 4 different species in our goal reaction, right? We wanted to determine the delta H for the reaction of carbon with water to produce carbon monoxide and hydrogen gas. Let me add my phase there. All right, and so what you want to do is you want to you want to identify, for example, okay, we need solid carbon on our reactant side. And in this first reaction, we have solid carbon on our reactant side. So that's good. We don't need to manipulate this equation. You'll notice, however, that we have over here, we have carbon monoxide on the product side, and here we have carbon monoxide on the reactant side. So it's on the wrong side of the arrow, and you'll notice that we have a stoichiometric coefficient of 2. So here, for this reaction, we need to do 2 things. First, we got to take it and we got to flip this situation. Right, because we need carbon monoxide on the product side. So I'm going to swap sides with the reactants and the products. And when I do that, my delta H retains the same value, but now has a different sign. So it was originally negative. When you flip it, you got to make it positive. The second thing I got to do, I'm glad that I have carbon monoxide on my product side, but now I still have the wrong stoichiometric coefficient. I only want 1 mole of carbon monoxide being produced in this reaction. So I need to take this and multiply everything in this reaction by 1/2. When I do, this will give me 1 mole of CO2. Oops, did not mean for that to be green. 1 mole of CO2 plus, or no, not plus, becoming 1 mole of carbon monoxide plus 1/2 mole of O2. Now, you know from earlier in the semester, I'm like, you can't ever have fractions in your balanced chemical equation. It's got to be integers. That still holds true. But we do know, we have seen in the past, that you introduce fractions in order to get to your answer, and that's what we're doing here. We won't leave the fraction in there at the end, but we do just have to roll with it for now. So now we got to divide. Since we multiplied our reaction by 1/2, we also have to multiply our change in enthalpy by 1/2. So dividing 566.0 by 2 gives us a positive 283.0 kilojoules per mole. And now what I'm going to do is I'm going to take this, because this finally we have, you'll notice, 1 mole of carbon monoxide on our product side. I'm going to take this and I'm going to add it to my my situation here. Oh. So I'm going to take that manipulated equation that we had and add it to the mix here. All right, so here we've got carbon dioxide gas producing carbon monoxide gas plus 1/2 O2. So I'm going to move this delta H over just a little bit. There we go. Oops, okay, sorry. All right, so that manipulated equation, I'm going to move that over here and add it underneath this equation. And here's why. Okay, so here, hang on, our delta H here, our manipulated delta H is 283.0 kilojoules per mole. And here's why I want to do that. Sorry, it should be carbon monoxide on the product side. Again, the reason why we're doing this is we have carbon monoxide in place. Correct number of moles on the correct side of the chemical reaction. We also have solid carbon in place. Correct moles, correct side of the reaction. What we want to do next is we need to place our water and our hydrogen. For that, we're going to need to look at our third reaction, which is right here. Now, when you look at our third reaction, we need hydrogen. We need 1 mole of hydrogen on our product side, and right here, we've got hydrogen on our reactant side. So we're going to do a couple manipulations. First, we are going to flip this guy around, and I see now that I forgot my sign right there. That should be a negative. So first we're going to flip our reactants and our products. So our sole reactant here is 2 moles of water, and our products now will be 2 moles of H2 plus 1 mole of water. And our delta H, now that we're flipped, same value, different sign, will be plus 483.6 kilojoules per mole. All right, and then next, you'll notice that we have 2 moles of H2O, or sorry, of hydrogen on our product side, but we only want 1, so we are going to multiply everything by 1/2. This will give us 1 mole of water vapor producing 1 mole of hydrogen gas plus 1/2 mole of oxygen this produces, let's see, we got to cut our delta H in half. So 483.6 divided by 2 is positive 241.8 kilojoules per mole. And now that hydrogen is right where we want it to be, we're going to take this and we are going to add this to our, whoa, not that one. Not that one either. Where's the one? Oh, here we go. Sorry, my slide got messed up. There we go. Ah, Kate, great question. Kate, great question. When you multiply the whole expression, the whole reaction by like 1/2 or by 2 or whatever you're doing in the problem, that 1/2 or that 2, that integer value is not a measured quantity, and so the delta H retains its original number of sig figs. All right, so this gives us water vapor. So the answer is yes, I am applying the rules for sig figs, but the rule for sig figs, when you multiply a number that wasn't measured, is you just keep your original number of sig figs. And this is a delta H of positive 241.8 kilojoules per mole. All right, so you'll notice here we've got hydrogen, 1 mole of hydrogen on the product side. But in addition, we actually, through pure serendipity, also have 1 mole of water on the reactant side placed where we need it. So at this point, we have found and placed each one of our reactants and products on the side of the reaction that we need them in the correct number of moles. Now, this doesn't necessarily mean that we're done. We need to make sure that everything else cancels. All right, that is the key to this situation. And so one thing that you'll notice instantly is carbon dioxide. You've got 1 mole of carbon dioxide on the reactant side, 1 mole on the product side, so these two quantities cancel. All right. Now, the second thing you'll notice is you have 1 mole of oxygen on the reactant side, and on the products you have 1/2 plus 1/2, or 1 whole mole of oxygen. So these O2s cancel these O2s, and when we go and add all of these together, what we end up with is solid carbon 1 mole of solid carbon plus 1 mole of water vapor produces 1 mole of hydrogen gas, and 1 mole of carbon monoxide. And even though I wrote it in a different order down here, it is the exact same equation that we want to find the delta H for, and that delta H we can find by adding these 3 delta H's together. So let's go ahead and do that. We have negative 393.5 plus 283.0 plus 241.8. This gives us a delta H that is 131.3 kilojoules per mole. You'll notice that our sig figs are totally correct because each number we added had its last significant digit in the 10th place, and our answer does as well. So this will be our final answer for this problem. So Ludwig and everybody who's hanging, that is how you handle that problem. I always recommend starting by trying to place every reactant and product exactly where it needs to be in the correct quantity. So manipulate those reactions around. And then once you've set up your reactants and products right where they got to be, then you look and see, does everything cancel? If it doesn't, then that means you'll have more reactions that you'll need to bring in to make sure everything cancels. Okay. So that is that. Isabel, you have been waiting patiently. Let's see. Could you explain the charges on the lab for question 2? Isabel, quick question. Are you asking about are you asking about question 2 on the worksheets? Where, or I guess the question that I have is where is your question 2 originating from? So I want to know so I can pull up what you are asking about so I can give an intelligent answer. Okay, awesome. Here, let me pull that up. There's the worksheets. Wait, hang on. Oh, I'm like, this doesn't look right. I went to ELAB 2. I'm assuming you're actually asking about ELAB 4. Here's the correct worksheet. All right, let's see. Write a balanced chemical equation for the net ionic equation for each reactant to perform on scratch paper. All right, so like for example, so for this reaction or these reactions in this lab, let's see, your question was explain the charges. Yes. Okay. So with this lab, almost all of the metals used in this lab only take one charge. There's a few that can take multiples, but almost everything takes one type of charge. So, for example, with zinc, you're dealing with zinc And as an ion, it's going to be 2 plus. When you have a reaction with silver, it'll be silver and silver 1, charge of positive 1. Those are transition metals, but they always have predictable charges no matter what. The other metals like magnesium and aluminum, the main group metals, you determine from the periodic table. There are other transition metals that they use that that can take multiple charges, but the charges that you're dealing with in this lab, they go with their common one. So you'll have cobalt metal and cobalt 2. You'll have gold and gold 1 when you're dealing with it as an ion. I'm trying to see if there's any other transition metals. You'll be dealing with copper and copper 2. Copper has can have multiple oxidation states, but you'll be dealing with copper 2 here. I'm just going over to see, are there any other deals? All right, that looks like all of them, and then all the main groups metals, you can figure out those charges from the periodic table. But this is what you're looking at. Whoops. For the transition metals, because again, the type of reactions that you're exploring here are what are known as single displacement reactions. So you have some metal with some ionic compound AX, and these are reacting to make A as an element plus a metal X. And so both of these are ionic. And this right here, these are the charges that neutral M takes in MX. And just for example, if you had the reaction sodium plus zinc chloride, the products here will be zinc metal plus sodium chloride, and then to balance it, you go like so. So that's how you take that. And Isabel, great question. The specific charges. Oh, there's another. Sorry, I'm gonna add one more transition metal to this. There's one that I missed. Lead. It'll be Pb and Pb2 plus. There we go. That should be all of them. That should be able to get you. Yes, Isabel, 100%. The charges totally change because these are all redox reactions. So you have electrons changing hands, and that will change the charges of the ions. All right, Kate and Ludwig, I totally can. Give me 1 second as I log in. Isabel, you are so totally welcome. It is. I just want you all to know that it makes my heart glad when humans roll in and ask questions, because I know this material is challenging and it's difficult, and I have students reach out to me who, are saying they're frustrated, they're struggling in this class, like what to do, and this is the first thing I tell them: come to office hours. I'm hanging out six hours a week, just waiting, hoping that you guys show up and ask questions, and it really, there's nothing I enjoy more than helping. So thank you for enriching our time and asking some great questions. I appreciate you showing up. Let's see. I am in the process of logging on to my account with the publisher so I can pull up the book so we can do some homework problems. Okay. Oh, cool. Chapter 5. Chapter 5 has some cool stuff in it. Let's see. All right, starting with 43. All right, let's take a look. So this is chapter 5. Problem 43. All right, let's see. An automobile has a maximum tire rating of 30 psi, 38 psi. The tire is inflated to a volume of 11.8 liters at a gauge pressure of 36 psi and a temperature of 12.0 degrees Celsius. Driving on a hot day, the tire warms to 65.0 degrees and its volume expands to 12.12. Does the pressure in the tire exceed its maximum rating? Note the gauge pressure is the difference. Wait, hang on, that might be important. The gauge pressure is the difference between the total pressure and the atmospheric pressure. Okay. So, this one's a little bit of a thinker because of that whole twist with gauge pressure. Essentially, so let's talk about this problem. The tire is rated at 38.0 pounds per square inch. All right, and then we're given a set of initial conditions, right? We're given a set of initial conditions. Let's see. So we're told that initially we have a volume of 11.8 liters. Our initial temperature is 12.0 degrees Celsius. And our gauge pressure is 36.0 psi. And I'm just going to put gauge. Our final pressure, or sorry, our final set of conditions, we're told that, well, our temperatures increased to 65.0 degrees Celsius, and our volume has expanded to 12.2 liters. And then we're asked, does this pressure in the tire exceed our maximum rating? So essentially, the question that we're asked is P2 more than 38.0 psi? That's the question that we're being asked here. And then they slip us this weird little note that gauge pressure is the difference between the total pressure and the atmospheric pressure. So gauge is the difference between the total pressure, P total, minus our atmospheric. And then we're told that atmospheric pressure in these conditions are 14.7 psi. So that means that the total pressure is the gauge plus atmospheric. So that means that our actual initial pressure is going to be 36.0 psi plus 14.7 psi. So this number is going to be a little higher. So 36.0 plus 14.7. Whoops. 36 plus 14.7. There we go. So our initial pressure in the tire is actually 50.7 psi. All right. So we need to find P2. Right, that is what we're after. And whenever you're given a mix of initial and final conditions, then we'll have P1 times V1 over N1 times T1 is equal to P2 times V2 over N2 times T2. All right, and we have been given initial pressure, volume, and temperature. We've been given final volume and temperature. Now you'll notice that we haven't been given any information about moles, but you'll also notice that it hasn't said anything about the tire leaking, so we can assume that the number of moles in the tire has not changed, and so moles cancel, allowing us to solve for our final pressure. So let's go ahead and do some algebra. We've got, whoops, let's open a new slide maybe. So we've got P1 times V1 over T1 once we cancel out moles is equal to P2 V2 over T2. Now we've got to do some algebra. We got to isolate our final pressure, so we're going to multiply both sides by T2 over V2. So that they cancel out of our right side. So we get our final pressure is equal to P1 times V1 times T2 over T1 times V2. Now, before we can plug these things in, we have to do a few unit conversions. Our final temperature was 65.0 degrees Celsius. We need to convert this to Kelvin before we use it in the combined gas law. So T2 is equal to, let's see, 65 plus 273.15, 338.15 Kelvin. Our last sig fig in this number is in the first decimal place because we're adding, and that was our final temperature's last significant digit. We need to do the same for T1 here. T1 was like, I think it was 12. Yeah. 12.0 degrees Celsius plus 273.15. So this comes out to be 285.15 degrees Celsius. Again, last sig fig is in that first decimal place. Okay, we are ready to solve. So our pressure, initial pressure, we take that gauge rating and add 14.7. So it was 50 something, 30. No, that's the rating, not 38. It was 36.0, 36. So our initial pressure in the tire is 50.7 psi times our initial volume, which is 11.8 liters, times our final temperature, which is 338.15 Kelvin. Over our initial temperature, 285.15 Kelvin, times our final volume, which is 12.2 liters. Ludwig, great question. As long as you're using the same pressure units, you will be totally fine. I believe. Yeah. Okay. So let's crunch our numbers. So we have 50.7 times 11.8 times 338.15 divided by 285.15 divided by 12.2. I'm going to double check this real quick. So 50.7 times 11.8 times 338.15 divided by 285.15 divided by 12.2. Yep. Okay. So our pressure. Whoops. Comes out to be, and rounding to 3 sig figs, 58.2 psi. But you'll notice that our tire gauge pressure is rated at 38, but this is not gauge pressure, this is total pressure. Our final gauge pressure is equal to the total pressure, 58.2 psi, minus the atmospheric pressure, which they told us was 14.7. So 58.2 minus 14.7 is 43.5 psi, and we can now that we've calculated the gauge pressure, this exceeds the rating of 38.0 psi. So that is that problem. Totally. That is problem 43. Let's see. Let's hit up the next guy, 46. Trying opening my office window, but forgot that the AC unit is literally on the other side of the window, so I opened it and it was like super loud. Yes, that was a tricky one. Dude, props to you guys for attempting it though. All right, let's see. There's a huge benefit in doing problem types that you've never seen before. It's the best way to prepare for a test. Okay, let's see. So we're going to hit up again another chapter 5. Whoops, number 46. All right, a 1 liter container of liquid nitrogen is kept in a closet measuring 1 meter by 1 meter by 2 meters. Oh, I already see one trick that they're doing. Assuming that the container is completely full, that the temperature is 25 degrees C and that the atmospheric pressure is 1 atmosphere, calculate the percent by volume of air that is displaced if all the liquid nitrogen evaporates. All right. So let's go ahead and get into this. So we have a 1 liter container. So here's the thing. All right. Here's the deal. The first thing that you want to do whenever you're doing a problem for the first time, is you want to identify what you're trying to find. Right? And we're asked to calculate the percent by volume of air that is displaced if all the liquid nitrogen evaporates. All right? Percent by volume is the volume of the air that's displaced, which is going to be equal to, the volume of air that's displaced will be equal to the volume of nitrogen. Right? Because that gas is moving into the space, so that volume that nitrogen takes up is going to push out, displace the air, divided by the total volume times 100%. This equation gives us a roadmap for finding that thing that they're asking for. It actually breaks it down to 2 chunks. We need to first find the volume that nitrogen is going to occupy, and 2, find our total volume. All right, and once we have those, we can calculate the percentage. All right, now, here's a cool thing. The total volume, so let's start there. The total volume is the volume of the closet, right? And the closet, we were told, is 1 meter by 1 meter by 2 meters. And how do you find a volume? You multiply height times height times width times base, right? So the volume of the closet, the total volume, is 1 times 1 times 2. So 2 cubic meters. Now, we already know enough to know that we're typically dealing in volumes of liters, right? We really don't handle cubic meters all that much. So we might have a unit conversion in our future. Actually, we definitely have a unit conversion in our future, right? Because we're told we're given a density of liquid nitrogen in grams per milliliter. So we are going to need to convert cubic meters to something else. So let's do it. Now, the thing to remember whenever you're converting a weird unit like cubic meters is you want to remember this golden nugget. 1 cubic millimeter, 1 cubic centimeter is equal to 1 milliliter. So we want to convert cubic meters to cubic centimeters. Then it'll be in milliliters, and then we're off to the races. So we know the unit conversion for between meters and centimeters, right? 1 meter is 100 centimeters. And if you do this 3 times, you will cancel your cubic meters. Right, the 1, 2, 3 together will cancel your meters cubed, and you get a total volume of 2 times 10 to the 6th cubic centimeters or milliliters. So that's going to be more useful. So this here is our total volume. We've got our denominator. We're halfway there. Now we have to find the volume that our liquid nitrogen will occupy once it joins the gas phase. All right, so let's take a look at how we find that volume. Once we know this, we're off to the races. So what do they tell us? They tell us that we have 1.0 liters of liquid nitrogen, and they tell us the density of liquid nitrogen is 0.807 grams per milliliter. All right. They also tell us that the closet has a temperature of 25.0 degrees Celsius, and that the pressure is 1.0 atmospheres. We also know the volume of the closet because we just calculated it, right? It has a volume of 2 times 10 to the 6th milliliters. Now, this is where you might be tempted to use to use the combined gas law. Because it looks like you have an initial volume, right? And then we know a final volume, but you can't. You can't use the gas law, the combined gas law here, because this is 1 liter of a liquid, right? And we're dealing with a gas. But you'll notice down here we have a temperature, a pressure, and a volume. We're almost set Let's see. Okay, let's do some thinking. Because these 3 quantities apply to a closet. These 2 apply to nitrogen as a liquid. All right, let's do some thinking here. All right, we want to know. So the process is we have a sample of I know this looks like a weird house. It's a gas cylinder. Okay, now it just looks like someone flipping me off. Which might be the rest of the class. Who knows? So we've got liquid nitrogen. What's going to happen is it is going to get sprayed out as a gas it is going to become gaseous nitrogen. And we need to know what volume will it occupy. Right? That liquid nitrogen, when you open up the canister, it's going to spray out, become a gas, and we want to know what volume will it occupy. Now, we know that the pressure of the room it's being released into has a pressure of 1.0 atmospheres. We know it has a temperature of 25 degrees Celsius, and it will become that room temperature as it expands out. We know our ideal gas constant, R, is just a constant number. The one thing we need, we could use the ideal gas constant to find the volume it occupies if we knew how many moles of this situation we had. And check this out. The volume of liquid nitrogen together with the density, these two things can give us grams of nitrogen. And then we can use its molecular weight to go from grams to moles. So that is how we get moles, and moles is how we find the volume it'll occupy, the volume that'll be displaced. That lets us tie back in to the what the question was originally asking. So let's start by finding our moles of nitrogen. So we have a density of 0.807 grams of N2 over milliliters, and this is being stored, the liquid nitrogen, in a volume of 1.0 liters. Now we need to apply a unit conversion to convert from liters to milliliters. 1 milliliter is 10 to the negative third liters, so liters cancels here, and milliliters cancel here. All right, now that we've gotten rid of our volume unit, we can convert from grams of N2 to moles of N2. 1 mole of nitrogen has a molecular mass of 28.2 grams. Right? So now we can crunch our numbers. 0.807 times 1. 0.807 times 1 divided by 10 to the negative third divided by 28.02 gives us, so we have 28.80008565 moles of N2. That is quite a lot of moles of N2. We can keep 3 sig figs. And now that we know moles of N2, we can use the ideal gas law, PV equals nRT, to find our volume. We need to divide both sides by pressure. To get our volume isolated on one side of this equation. So we get volume is equal to our number of moles. I'm just going to round it there because there's so many zeros after it. It's going to be inconsequential. 0.08206 liter atmospheres per mole Kelvin. Temperature, we were given a temperature of 25 degrees Celsius. When you convert that to Kelvin, it'll be 298.15 Kelvin with its last sig fig right there, all over 1.0 atmospheres. 1.0 atmospheres, right? I'm just making sure I wrote down the right number of sig figs. Yes. All right, so this volume that nitrogen gas will occupy is, let's see, 28.8 times 0.08206 times 298.15 divided by 1. Something's off. Well, I'm gonna write down what I've got, but I feel like something's wrong. Let's see. Well, the value is 704.6. But we can only have 2 sig figs, right? Because of down here. So I'm just going to put 2 lines there. I think something's up. Okay, let me just check. But I feel oh, no, we're fine. We're totally fine. I spaced out. Okay, we're totally good. Oh my gosh. Okay, one of those moments where I had like psyched myself out, but I was remembering things wrong. So, okay, so we've got our volume of N2 gas. Now, let's calculate our percentage. So, rolling back to where this problem started. Our percent, oh wait, sorry, new slide. Our percent by volume is the volume that nitrogen gas will occupy over our total volume times 100%. Now, the volume we just calculated for nitrogen, 704.6 liters, 2 sig figs in the numerator, over our total volume, which is 2 times 10 to the 6th, cubic centimeters. Now, before we can crunch these numbers, we need to have the same volume units in play. So I'm going to convert 2 times 10 to the 6th cubic centimeters to liters. So first, I'm going to convert cubic centimeters to milliliters, and that is a 1-to-1 ratio. Next, I'm going to convert milliliters to liters. So milliliters cancel, and cubic centimeters cancel. And when you crunch your numbers, you'll see that the volume of the closet is 2,000 liters. So now we can calculate our percent volume. Oh, you know what, Kate? You are totally right. You're totally right. Oops. You're so right. This should have been 2.0. So I'm just going to put 2 lines under this because that should have 2 sig figs. So 704 over 2,000, but 2 sig figs. Numerator has 2 sig figs. Times 100. Now our volume units cancel out proper. And I don't know, this is probably going to linger somewhere around 40-ish%. Let's see. Oh, 35. So the percent volume displaced by the release of nitrogen gas is 35% of the volume of the closet. How's that for another whopper of a problem? Honestly, chapter 5 homework problems are hard, and they're really good. They're excellent practice. Let's bounce to the next one, which is number 48. Oh, let's see. Yeah, Isabel, totally. Actually, this is the perfect time to jump in because we haven't started the next lengthy. No, Kate. Honestly, these problems are like next level hard, and they're really good for like teasing, like making you think about things in unconventional ways, pulling in different concepts, like even percent by volume. You have to think, okay, what does this mean? And then doing calculations like using the density and the volume of nitrogen in its liquid state to find the number of moles. Like it's just they're very, very hard, which is why they're so good, and which is why I'm glad you're diving into them. Okay, Isabel. Okay, awesome. Awesome, Isabel. Great, um, great example. Okay, so copper reacting with silver nitrate. So here's the thing for lab 4. Lab 4 is it's sometimes called the activity series, and these types of redox reactions are called single displacement reactions. All right, they're called single displacement reactions, and they all follow this general category. You have some metal reacting with some ionic compound that I'm going to call AX, and the metal and the A, whatever that is, will exchange places where you'll make A as an element plus an ionic compound MX. So, for example, copper metal reacting with silver nitrate. Whoops. All right. In this specific reaction, so you observed a reaction for this one. Your M is copper. Your A is silver, and your X is nitrate. All right, so that means on the product side, oh wait, let me get my colors straight here. On the product side, A is just going to be straight up silver metal. All right, now to figure out your M and your X, we've got to look at what types of ions those are going to be. Now, X is unchanged. X is the same ion on the reactant side and the product side. So for X, we're dealing with nitrate, which has a charge of -1. And Isabel, you'll remember, let me see if I can find it. Nope. That slide where I talked about all the charges. Here it is. This is what you want to reference when you're looking at, okay, what are these going to become? Copper, right here. Copper becomes a copper 2 cation, all right? So this is what you reference for those transition metals when you're not sure what ion they turn into. Take a look at that. There we go. So copper there we go. Copper is going to become C. Hang on, where am I? There I am. Copper is going to become Cu2+. So on the product side, the MX is going to be CuNO3 2 because we need 2 nitrates to balance with our copper. All right, so these are the reactants and the products of this reaction, and then we have to balance like normal. All right, you'll notice that we have 2 nitrates on our product side, so we need to multiply silver nitrate by 2. Now nitrate's balanced, but now we have 2 silver on the reactant side, and we need 2 on the product side, so we multiply silver by 2. All right, so this would be your balanced chemical equation for the reaction that takes place between copper and silver nitrate. Essentially, whatever metal is in the ionic compound, your AX, just becomes the element, just itself as an atom, as a metal. And then you've got to figure out what charge will your M have on the product side, and that'll tell you your ratio between M and X. Isabel. Not necessarily. They can. Um, they can, but they don't have to. The reason why it started with the reason why we knew it started with a charge of +1 is because here it's paired with one nitrate. So since nitrate is a -1, that means that silver, if it's balancing with one nitrate, has to be +1. So the reason why we knew that was because nitrate was -1. But you could have a situation, for example, where you start with something like this. You could start with this guy on the starting side, and chloride we know is a -1, and in this compound we have 2 of them. So that would tell you that to balance with 2 negative chlorides, zinc here would have to have a charge of +2. So they don't have to start with -1, but the nice thing is on the reactant side, you will automatically be able to tell what the charge is based on the charge of the anions and how many anions they're paired with. Does that make sense? Dude, Isabel, I'm so glad I can help. Thank you for continuing to ask too. And I think that's one of the pitfalls that I run into. Sometimes students, when they ask a question, are sheepish to ask a second. And I so want to encourage you to keep asking until you get all your answers, all the answers you need. Don't have to worry about asking again, even if it's about the same topic. Okay. All right. Next, chapter 5 homework question that we have lined up is number 48. So let's take a look at pressurized. Okay, so here's the problem. Pressurized carbon dioxide inflators can be used to inflate a bicycle tire in the event of a flat. These inflators use metal cartridges that contain 16 grams of carbon dioxide at 298 Kelvin. I'm so sorry. I'm not yawning because I'm bored. That yawn was born of pure exhaustion. I took a 2-year-old to Costco today and in the heat, and it sucked so much life out of me. Okay, anyways. So we're told to what pressure in PSI can the carbon dioxide cartridge inflate a 3.45 liter mountain bike tire? Note that the gauge pressure is different than the total pressure and atmospheric pressure. or is the difference between the total pressure and atmospheric pressure. In this case, assume atmospheric pressure is 14.7 psi. All right. As always, whenever you're dealt a problem that you're not exactly sure how to solve, this is how you get to the answer. Identify what you're trying to find. All right. So there we just look for the question mark. To what pressure? Whoops. I don't want that in blue. To what pressure can the CO2 canister inflate the bike tire? Right? Let's see what we're given. All right, what are we given? So we're given that we have don't want that to be in blue. Hang on, here we go. We're given that we have 16.0 grams of carbon dioxide held in this canister. We're told that our temperature is 298 Kelvin. And we're told that we have a bike tire whose volume is 3.45 liters. All right, so we're being asked to find P. We know that PV equals nRT. And so far, we've been given temperature, volume. We always know R. So again, this comes down to we need our moles. We don't have moles, but we do have grams. So let's convert our mass of CO2 to moles, and then we'll be able to find pressure. So carbon has an atomic mass of 12.01. Oxygen is 16.00, but we've got two of them. So this will come out to be 44.01 grams of CO2 are in 1 mole. So 16 divided by 44.01 comes out to be 0.36355. We can only keep 3 sig figs at the end of the day. This is moles of CO2. Now that we know moles, we can find our pressure because we divide both sides of this equation by volume. So our pressure will be equal to our number of moles, 0.36355. Only 3 sig figs here. Times R 0.08206 liter atmospheres per mole Kelvin. Times temperature, 298 Kelvin, all over our volume of 3.45 liters. 0.36355 times 0.08206 times 298 divided by 3.45. Pressure, therefore, is 2.5, let's see, 3.6, so 2.58 atmospheres. Now, you'll notice that they put some conditions on the answer. They asked, to what pressure and psi can carbon dioxide cartridge inflate this mountain bike tire? And they said, note that gauge pressure is the difference between the total pressure and atmospheric pressure. And they wanted the answer in psi. So this is good, but this is total pressure. They want the gauge pressure in psi. So first, we got to take our total pressure and convert it to psi. So 2.58 atmospheres. 1 atmosphere is 14.7 pounds per square inch. So we got 2.58 times 14.7. So this comes out to be 37.9 psi. All right. That is a total pressure. Now the gauge pressure is total pressure minus atmospheric pressure. So we take our total pressure, which is 37.9 psi, and subtract 14.7, because that's what they told us that the atmospheric pressure is, or told us to assume that. So the pressure on the bike gauge, or that the bike gauge will read, will be 23.2 psi. And that is what the gauge will read when we inflate our bike tire with one of those CO2 canisters. And that is the answer to number 48. I think we're halfway through our original requests, or almost halfway through. We were asked, you asked 7 questions and we covered 3. So let's jump to 56. Chapter 5, number 56. Let's take a look. A sample of dinitrogen monoxide gas has a density of 2.85 grams per liter at 298 Kelvin. What is the pressure of this gas? Interesting. In millimeters of mercury. All right. Buckle in. We're going to do some algebraic sleight of hand. All right. I want to start by asking you all a question. Do you know the difference between molarity and density? Do you know the difference between molarity and density? Molarity is moles over liters. Density is grams per liter. So it can also be grams per milliliter. Yeah, exactly. Kate, you nailed it. Actually, you typed it before I could write it out. The way you convert, yeah. Ludwig, exactly it. It's the difference between mass versus moles. The denominators are both volumes. They're the same. It's just the numerators are the difference. The way you convert from molarity to density, or vice versa, but in this case, moving molarity to density, you can do it if you just multiply by the ratio of grams to moles, right? Then they're equal. And this, grams per mole, is the molecular weight. All right, so that's cool. That's interesting. But you may be wondering, okay, well, what does this have to do with gases? Because clearly we're in Chapter 5. We're doing Chapter 5 homework. And I'm talking about molarity and density, but we're here in the middle of the gas situation, right? I want to ask you a second question. So the first was about really the difference between molarity and density. The second question that I have for you, oops, let's open a new slide. Here's the second question that I have for you, and that is, do you know where molarity, or let me rephrase this. Do you know that molarity is in the ideal gas law? And if you don't believe me, watch this piece of algebraic trickery. Ideal gas law, PV equals nRT. I am going to divide both sides of this equation by RTV. You can see volume canceling on the left side, RT canceling on the right side. This gives us a new expression. P over RT is equal to N over V. Dude, yes. Yeah, you see it, right? In the numerator, we've got moles. In the denominator, we've got liters. This is literally, you could rewrite this expression to say the molarity of a gas is equal to its pressure, the pressure of the gas divided by R, times temperature. This is an equation you can actually use as long as you're dealing with a gas. It won't apply to liquids or solids or anything. But for gases, it works. Now that I've shown this to you, let's take a look at what they're asking in problem 56 and approach it with new eyes. So in problem 56, let's identify what we're trying to find. They're asking us for the density. Oh, wait, no, that's 55. 56. They want to know what. They want us to find the pressure of NO2. All right, what is this pressure? And what we're given, which at first may have seemed not helpful at all, given what we've just been thinking about, we'll be able to connect the dots. We're told that the density of N2O is 2.85 grams per liter. And we're told that the temperature is 298 Kelvin. All right, now, with that equation that we just wrote, we saw that the molarity of our gas is equal to pressure times R times T, which means if we multiply both sides by RT, we get this new expression. The pressure of a gas is equal to its molarity times R times T. We know temperature, we always know R, and though we don't have the molarity yet, we can find it because we know how density relates to molarity. All right, so we have here 2.85 grams of N2O over liters. We can get our molarity if we convert from grams of our gas to moles. All right, so nitrogen has an atomic mass of 14.01. We got to multiply that by 2. Then add 16 for oxygen, so this will be 44.02 grams of NO2 in 1 mole. So we got 2.85 divided by 44. Divided by 44.02. Hang on, my calculator's wigging out. 44.02. All right, so this comes out to be our molarity, right? Because grams cancel grams. This leaves us with moles per liter. We have a molarity of 0.0647. Sorry, hang on. This is moles per liter. Now we have enough to find our pressure. We know our molarity. We know R. And we know our temperature, if I can squeeze it in here. 298 Kelvin. Dude, isn't it? It's pretty rad. So Kelvin cancels. Moles cancel. And liters cancel. Leaving us with atmospheres. I'm just making sure they didn't ask for a specific... Oh, they did. They asked for pressure in millimeters of mercury, so we'll have to do a unit conversion once this is through. So let's take 0.0647 times 0.08206 times 298. So this is 1.58 8 atmospheres. Then we got to do one last unit conversion because they want millimeters of mercury. So 1 atmosphere is 760 millimeters of mercury. Okay, oh, interesting. So our pressure is 1,202.446. We need 3 sig figs. 2's going to round down, though. So 1,200 only has 2 sig figs, so our correct answer with the correct number of sig figs will have to be in scientific notation. And that is our final answer for number 56. Again, another mind bender. I really feel like the chapter 5 homework questions, also the chapter 6 homework questions, are where Chem 400 really starts differentiating itself from 305. This is where general chemistry gets harder than the intro class ever got. So I'm really glad that you guys are working these problems because you're getting a taste for the next kind of level up of difficulty that you'll be facing, and I think a lot of students are blindsided by that when they hit exam 3. Kate, you are so welcome. Yeah, Ludwig, it's a really weird problem. Once you know the trick, it's not that bad, but if you've never seen it unpacked like this, then it becomes a real challenge, and that's why I assign this as homework to practice, because the students who do the homework are going to be stretched in ways that students who just look at my lecture and try to memorize the problems that I do, they're not going to be prepared to take the test. So this is a crucial part of studying. I'm so glad you guys are in it. Kate, great question. I find that reading the textbook works for some students and not for others. So it really depends upon your reading style. Some students get a lot out of reading the textbook. Some students don't really. So if it works for you and if you get stuff out of it, totally do it. What works for, well, I don't know if I can say this works for every student, but what every student needs. Yeah. So if you're finding some of the concepts are difficult to absorb, that's where, try reading it. If that helps you, awesome. If not, you can always bring those questions to office hours, and you can even say okay, I'm really struggling with understanding this. Could you try explaining it to, or could you unpack this or help me see it from a different perspective? And I can do that. If you have a conceptual thing, I don't have to just work problems. I can do okay, conceptually, here's this topic. Here's, Dalton's law of partial pressure or whatever the concept is. And even do a little mini kind of review of it in office hours. This is for all types of learning, not just problem solving. That being said, I do recommend problem solving as the primary study tool, because this will drive you to the concepts where you need help, where you need review. Because often if you don't know how to solve a problem, it's because there's some conceptual component that hasn't been internalized yet, and the act of solving a problem often serves to fill in those gaps in understanding. So I think problem solving is the best way to study, especially since that's what you will be tested on, is your ability to solve problems. So it's also, in a lot of ways, the most relevant as well. Totally. Okay, let's take a look at problem 64. Okay, yeah, we're in Dalton's. So a 275 milliliter flask containing pure helium at a pressure of 752 torr. Oh, contains pure helium at a pressure of 752 torr. A second flask with a volume of 475 milliliters contains pure argon at a pressure of 722 torr. If the two flasks are connected through a stopcock and the stopcock is opened, what is the partial pressure of each gas and the total pressure? All right. So this one is Dalton's law of partial pressures. And we have to understand what is going on. Let's see. Yeah, totally. That is actually the equation that we were using earlier, right? For it comes from that equation, which has density in it. After you use the molecular weight, you can derive the equation that you just wrote, which is another cool one. Okay, so we need to understand what is going down in problem 64. So we have two flasks. That are separated by this stop clock, which we can open and close. All right. And on this side of the flask, on this side of the flask, we have one volume and one gas, and on this side of the flask, we have another volume. Actually, we can do that in yellow. So on so over here we've got argon gas. Over here, what did it say? We have helium. All right, and the helium side has a volume of 275 mils. And right now, when they're separated, it has a pressure of 752 torr. All right, and the argon side has a volume of 475 mils, and a pressure of 722 torr. Now, what's going to happen? All right, what's going to happen in here? Whoops. So these two are separated right now. What's going to happen is we are going to open this situation. We're going to open the divider so that the helium and the argon are going to mix. All right, so we are going to remove the divide, open the pathway, and what is going to go down is helium is going to flow over to the argon side and fill up the whole thing, and argon is going to flow over into the helium side and fill up the whole thing. So both gases, argon and helium, after we open things up, oops, let's get down to a more normal brush size. So argon and helium fill the entire volume. After you open up that stop path, they both rush over to both sides and they fill the entire volume, which is, that entire volume is 275 plus 475 milliliters, right? So this adds to 750, and again, this is significant. 3 significant figures because we have our last significant digit in the ones place. Milliliters. All right, that's important to know that that's the volume that they occupy. All right, this is our final volume, V2 for helium, which equals V2 for argon. That is 750 milliliters with 3 sig figs. What you have here is, this is V1 for helium. This is V1 for argon. This is P1 for helium. This is P1 for argon. Now, they want to know what the total pressure is over in the green town. All right, so our total pressure is going to equal the partial pressure of helium plus the partial pressure of argon. All right, and the reason why I put 2's there is you've got your initial pressure, initial volume. We've got a final volume for each, and what we need, they want us to determine the partial pressure of each. We can determine that from the combined gas law because we've got P1, V1, and V2, so we can solve for V2. P2, sorry, and then once we have that final pressure for helium and argon, we take those 2 partial pressures, add them up, and that will be our total pressure. All right, so that is understanding conceptually what is going on in this problem will lead us to how to deconstruct it, how to solve it. So, starting with helium. Let's start with helium. Again, going from the combined gas law, P1 times V1 over N1 times T1 is equal to P2 times V2 over N2 times T2. Again, they haven't mentioned anything about temperature or moles. So we are assuming those are being held constant. We actually know moles are. They didn't mention any leak. They didn't mention any temperature change either. So this simplifies down to P1 times V1 equals P2 times V2. If we divide both sides by our final volume, we'll get an expression for the final pressure for helium, which is initial pressure times initial volume over final volume. All right, now for helium, our initial pressure was 752 torr. Our initial volume was 275 milliliters. And our final volume was 750 milliliters. But again, we have 3 sig figs in this number. The cool thing here is we don't have to convert our volume to liters as long as they're both the same. Torr is also works totally fine. So we have 752 times 275 divided by 750 gives us a final pressure for helium of, let's see, 3 sig figs, 276 torr. So this is right here, the partial pressure of helium. We can do the exact same calculation for the partial pressure of argon. It's the same derivation. It's P1 V1 over V2. Our initial pressure for argon was 722 torr. Our initial volume for argon was 475 milliliters. Final volume, 750 milliliters. All right, so now we're ready to crunch our numbers. 722 times 475 divided by 750. Again, remembering that we have 3 sig figs in our denominator. Gives us 457 torr. This is our partial pressure of argon, because they wanted the partial pressure of each gas. And now they want to know the total pressure, which is the sum of both partial pressures. So here we have 276 plus 457. Make sure they didn't specify a unit. They didn't, so we don't have to convert to atmospheres or anything. 276 plus 457. 733 torr is our total pressure. All right, so this problem was actually, just to comment on it now that we're here at the end, this problem was really cool because they what am I saying? It incorporated two different gas laws at once. Actually, we needed to use the combined gas law because we had an initial volume and pressure, and then going to a final volume, we needed the pressure, and it involved Dalton's law of partial pressure. So this is kind of like a cool two in one combo. Isabel, no worries. So alrighty, so that is problem number 64. Let's see. All right, we only have two more in this request block. We've got 72 and 77. Ludwig, great question. Here. Actually, let me pull this back. Okay. Okay, Ludwig, before I dive into your question, let me just reference the slide for Isabel. Is it this one? Nope. This one? Nope. There we go. Isabel. Isabel, this is the slide you want to use for determining the charges for the products in this lab. Pairings, you'll see copper and copper 2, gold and gold 1, cobalt, cobalt 2, silver, silver 1, zinc, zinc 2, and lead 2. So you just use these charges when you're figuring out what the charge on the product side is going to be. Let that be your guiding light. All right, and now I'm going to blank it out, but you can always pause the video, return to that moment. And okay, Ludwig, great question. How do we know to use the combined gas law and not the ATL gas law? So there's a couple ways. First, when you understand what's going on in the problem, you'll notice that each gas experiences a change in volume. At first, you have helium that's under one specific volume, right, 275, but then it's going to fill the entire thing. So helium experiences a change in volume. Argon likewise only occupies this half at the beginning, but by the end it occupies the entire thing. So when you experience a change, when you experience a change in volume, Ludwig, that's one indication that you'll need to use the combined gas law, because the combined gas law deals with initial and final states, whereas the ideal gas law is just there's no change involved. Anytime you're doing initial and final, though, combined gas law is the way to go. So that's one way you know you're dealing with the combined gas law in this problem. The second way you know you're dealing with it or I should say, second way you know that you're not dealing with the ideal gas law is you'll notice the ideal gas law is only useful if you are given all the information. And here in this problem, we're given volumes, we're given pressures. We always know what R is, but you'll notice that moles and temperature are totally not in the problem. If we were given one of these, if we were told the moles present, or if we were told it happens under this temperature, then we'd be able to use the ideal gas law. But if you're not given enough information to find 3 out of the 4 variables in the ideal gas law equation, then it's not going to be able to help you. And in this problem, we're only given pressure and volume and no other means of finding the other variables. So that's another reason why you know that the ideal gas law can't help you in this situation. All right, so that is that's how you know to use the combined gas law. 2 things: 1, not enough information to use the ideal, and 2, so that's why you don't use the ideal. The reason why you go to the combined is you've got initial and finals going on, and that's the dead giveaway. Yeah, I'm so glad. Okay, let's check out number 72. Oh, weird. Consider the chemical reaction. Oh, a splitting of water. So we've got a chemical reaction where we have 2 molecules of liquid water becoming 2 molecules of hydrogen gas and 1 molecule of oxygen gas. What mass of H2O is required to form 1.4 liters of oxygen at a temperature of 315 Kelvin and a pressure of 0.957 atmospheres? All right, this problem is so my style, it's not even funny. This is the type of problem I would write. Okay, so we want to know, they're asking us to find the grams of water. And they're telling us that they want to know what mass of water is required to form, give us a volume, 1.4 liters of oxygen. They give us a temperature, 315 Kelvin. Um, and they give us a pressure, which was 0.957 atmospheres. So notice we're not given initials and finals, so we know we're not going with the combine. They give us pressure, volume, and temperature. We always know R. So we can find moles of O2. When we use these three things. And why would we want to use moles of O2? So we can use the mole-to-mole ratio to go from moles of oxygen to moles of water, then from moles of water to grams. So let's take PV equals nRT and solve for N. So moles are equal to our pressure, 0.957 atmospheres, times our volume, 1.4 liters, times R, 0.08206 liter atmospheres per mole Kelvin, times temperature, which is 315. All right, now when you look at our units, Kelvin cancels, atmospheres cancel, and liters cancel, leaving us with moles. Let's crunch these numbers. 0.957 times 1.4 divided by 0.08206 divided by 315. So we produce 0.051831199. We can only keep 2 sig figs. I'm going to wait to round till the end. So this is moles of O2. Times, we want to convert from moles of O2 to moles of H2O, moles of water. 1 mole of O2, for every 1 mole of O2 produced, 2 moles of water had to react. Next we use, we use the molecular weight. To calculate the mass of water, because 1 mole of water has a mass of 18.016 grams, and we calculate that from the periodic table. So moles times 2 times 18.016. Wait. Okay. Moles times 2 times 18.016. Let's see, we can only have 2 sig figs. So this will come out to be 1.9 grams of water are needed to produce 1.4 liters of oxygen gas at 315 Kelvin under a pressure of 0.957 atmospheres. And that is number 72. 77 is the last queued up question. right, let's see. 77. Hydrogen gas, a potential future fuel, can be formed by the reaction of methane with water according to the following equation. Excuse me. And they give us a balanced chemical equation here, which is very kind of them. The equation is CH4 gas reacts with water vapor to produce carbon monoxide gas and hydrogen gas. Oh, and it's balanced for us already. That's nice. In a particular reaction, 25.5 liters of methane measured at 735 torr and 25 degrees Celsius mixes with 28 liters of water vapor measured at 702 torr and a temperature of 25 degrees Celsius. The reaction produces 26 liters of hydrogen gas at STP. What is the percent yield for the reaction? Okay, well, the first thing we got to do, as always, is identify what we're trying to find. And they ask us, what is the percent yield? Well, percent yield is actual over theoretical, right? Times 100%. So this equation narrows our focus down for us. We just need to find our actual yield, our theoretical yield. Once we know both of those, it's in the bag. What are we given? The first thing that jumps out to me in this problem, let's see if I can find it. Here we go. That we're given that the reaction produces 26.2 liters of H2 gas at STP. What is this? This is a volume. This is a pressure. And this is a temperature. In terms of ideal gas laws, this gives us our moles, right? If PV equals nRT, and we know temperature, volume, and pressure, we always know R, then we know moles. This is our actual yield in moles. All right? They don't explicitly tell us, but they give us enough information to find it. So that's the first thing we're given. It's the numerator. All that's left is the theoretical yield. Let's see what they give us in this problem. We're told that we have, for methane, one of our reactants, let's see, we're given a volume, 25.5 liters, measured at a pressure of 732 torr, and a temperature of 25 degrees Celsius. This allows us to find moles of reactant. We're told it mixes with, given a volume, 22.8 liters of water vapor at a pressure of 702 torr and a temperature of 125 degrees Celsius. This allows us to find our moles of water. Water is one reactant. Methane is another reactant. If you're wondering how you're going to find your theoretical yield, we have to do a limiting reactant calculation using these the ideal gas law to find our, well, which one's going to run out first, methane or water. So we can find the moles of each, find out theoretically how many moles of hydrogen it could be produced. Whichever one's smaller, that will be our theoretical yield. That's our denominator. Then we use the ideal gas law to calculate our numerator. And then we wrap it up and give it to a kid on Christmas. So let's start that theoretical yields calculation. Let's start with methane. Now, before we actually crunch our numbers, we've got some conversions to take care of. First off, temperature. We're given degrees Celsius. We need to convert this to Kelvin. So that'll be 298.15 Kelvin based on our initial temperature. The last sig fig is in the ones place, so that will have 3 sig figs. The second thing we got to convert is our pressure, because the ideal gas constant has pressure units of atmospheres, and we were given torr, so we've got to do a unit conversion. 760 torr is in 1 atmosphere of pressure. So 732 divided by 760 is 0.3 sig figs 963 ATM. With that, we can solve for moles, right? Because moles of CH4 will be PV over RT. So it'll be our pressure in atmospheres times our volume, which was given to us in liters kindly, 25.5 liters, over the ideal gas constant. This is liter atmospheres per mole Kelvin, times our temperature, which again only has 3 sig figs. So we're going to need to round this answer to 3. Let's crunch our numbers. 0.963 times 25.5 divided by 0.08206 divided by 298.15. Oh, hang on. 298.15. So I'm getting 1.0036 9126. That's how many moles of CH4 we have to begin with. Now we have to do the limiting reactant calculation, where we convert from moles of methane to moles of H2. And that unit conversion comes from our balanced chemical equation. 1 mole of methane will produce 3 moles of hydrogen. And we don't have to convert to grams. You can do a percent yield with moles in the numerator and denominator. And that is how I'm going to keep it for simplicity's sake. So if methane is our limiting reactant, then our theoretical yield will be 3.01 moles of H2. But we don't know if methane is our limiting reactant because we need to perform the same calculation with water. And just as we saw with methane, we have a couple unit conversions. The first one being, first unit conversion being temperature. So the temperature for water was 125 degrees C. We need to add 273.15. So this comes out to be 398.15 Kelvin. Last sig fig is in the ones place. We also need to convert our pressure, which was 702 torr. Let me just make sure that's correct. Yes, it was 702 torr. We need to convert to atmospheres. 760 torr or 1 atmosphere. 702 divided by 760. This is 0.924 ATM. Now we can calculate our moles of H2O because it is equal to, they are equal to pressure times volume over R times temperature. 0.924 atmospheres times our volume, which was given to us in liters, 22.8 liters, over R, 0.08206 liter atmosphere per mole Kelvin, times our temperature, 398.15 K. All right, 0.924 times 22.8 divided by 0.08206 divided by 398.15. This is 0.64480.528. All right, so again, we can only keep 3 sig figs, but these are our moles of water, 0.64480.528 moles of H2O. Next, we need to convert from moles of water to moles of hydrogen. And this ratio is a 1 to 3 mole ratio as well. So times 3. And 1.93 moles of hydrogen. Honestly, I don't remember what's on the other side. Slide. Oh yeah, 3.1. Okay, so this is, because it's lower, our theoretical yield. Now, we know what goes in our denominator. We know that we can calculate our numerator, but we still have to. So let's calculate our actual yield. Actual yield. We are given, oh, that's so nice. We don't have to do any unit conversions. We're given liters, atmospheres, and Kelvin. That is so stinking nice of them. Moles of H2 for our actual yield equal to PV over RT. Pressure, 1 atmosphere, because it's at STP. Volume, that gives 26.2 liters. R, always the same, 0.08206 liter atmospheres per mole Kelvin. T, 273.15. Okay. All right, let's crunch these numbers. 1 times 26.2 26.2 divided by 0.08206 divided by 273.15. So our actual yield is 1.17 moles of H2. Percent yield is actual over theoretical, which is, wasn't it 193? Yeah. 1.93 times 100. So 1.17 divided by 1.93 times 100 gives us a 60.6% yield. And that is how you do problem number 77. Wow. That felt like a marathon. I don't know about you. Those were some excellent problems. All very challenging in different ways. Using all of the gas laws we talked about. Just really next level. And great practice for exam 3. Dude, totally. What a problem. Indeed, that's enough to make me feel tired. That was a lot of work. And that's the thing too, is another reason why I liked these is we got to see several topics remixed, you know? It's like these homework problems were sampling beats from chapter 3 or chapter 4, right? This was a theoretical yield problem remixed in a gas law context, and a percent yield problem as well. It's just, you see how all these things, you really can't learn them in isolation. We learn them one at a time, but they are connected to the new things we learn in the future and remain connected. And really, I think it's, in my opinion, one of the strengths of the Tro textbook is that the problems really are integrate. The problems integrate multiple topics the new stuff in with the old, and you really get this kind of holistic feel for how these things kind of play out and play together. So it's I think it's excellent preparation for exam situations. Dude, I am so glad that it was helpful. Dude, and yeah, thank you for making it such a great office hours. Bringing your questions, adding insight. It's this time is dead if there are no students here to engage with, and so thank you for keeping me company, talking some chemistry, and again, I think I was watching the analytics on the stream today. Like, I think we topped out concurrent viewers at 7 was our peak moment. It was about 6 for a little while, but mostly 5, 3, 4. We're down to 3 right now. And I feel like, and I don't know, maybe people watch replays of the office hours to use those as a study tool as well, which might happen. But I feel like the live interaction is probably the most underused resource in this class. Between the 2 lectures, there's about 90 students, between 80 and 90 students, and we're maxing out tonight at 7, only for a hot second. But the cool thing is, up to 90 people could show up. Only 7 are, which means that for those of you who do show up, you get more personalized attention and interaction, and I can solve your specific problem. So keep coming. I'm so glad that you do, and I'm glad that you find it helpful as well. The number one thing I miss about teaching in person is the interaction with students, and I feel like this is the closest we come are the live stream office hours. It's more informal. There's no prepared material. It's not a lecture where I'm like, here are the things I'm telling you, but I'm here. You guys are saying, hey, what about this? What about this? And I'm on my toes. We're working through it, and you guys make it awesome. So thank you a ton. Oh, Rin. I'm so glad they're helpful. Actually, the one that we did tonight, I worked through 7 problems from the chapter 5 homework that were really, really, really hard. I'm actually going to post in Canvas and a link to this video say, yo, if you want very challenging homework problems on the gas law stuff, check these things out, because we like go through it in all gory detail. This is the first office hours where I was actually working the entire time. Like, there weren't any dead spots, where there weren't questions. The entire time we filled it, and some of these problems are really next level. So definitely go back, check this out. Today's in particular will be a very good study tool, preparing for the Chapter 5 material. Totally, and with that, it is now 10 o'clock. So I think I'm going to call it a night. Thank you, everyone who came out and made this good. Hopefully, if you're watching it, watching the replay, you'll find it useful. Again, a lot of really good problems tonight that we got to kind of flesh out and explore. I hope you all have an awesome weekend. I will catch you in lecture on Monday. Later, dudes.